All right, let us get going, continuing to talk more about logarithms, specifically some rules for logarithms. So there are three main rules for either expanding or compressing logarithms, and they are the following. If you have the logarithm of a product, so log with any base of x times y, that's equal to log base b of x plus log base b of y. This is often called the product rule for logarithms. We do need to say for logarithms because when you take calculus, there is a product rule for derivatives. And this is the product rule for logarithms. An example of this that I like to keep in my head is, for example, if you have log base 2 of 4 plus log base 2 of 8, that's going to equal log base 2 of 4 times 8, which is 32. And that's true because let's remind ourselves what things are. Let's do my favorite one first. Show me on your fingers. What's log base 2 of 8? Okay. Right. This many, 3. Log base 2 of 8 is 3 because 2 to the third is equal to 8. So this is 3. And then log base 2 of 4. So log base 2 of 4 is always the one that can be a little misleading. It's not that 2 times 2 is 4, although it is. It's that 2 to the second power is 4. So log base 2 of 4 is 2. And log base 2 of 32 is indeed 5, because 2 to the 5th is equal to 32. So that makes sense. 2 plus 3 is 5. Log base 2 of 4 plus log base 2 of 8 is log base 2 of 4 times 8. Cool. There's a similar rule for a logarithm of a quotient. It's called the quotient rule for logs. Log base b of x divided by y is log base b of x minus log base b of y. And a similar example, though not quite the same, if you had log base 2 of 16 minus log base 2 of 8, we would put those two logarithms together by dividing the 16 by the 8. So I want to point out, because I've seen this error happen a number of times in other classes, it's not going to be log base 2 of 16 divided by log base 2 of 8. It's not a log divided by another log. It's log base 2 of 16 divided by 8. So let's see, just to see what things are, log base 2 of 16 is 4, because 2 to the 4th equals 16. And log base 2 of 8 is, of course, our favorite. It's 3. We know it all the time. Just 2 to the 4th. And log base 2 of, let's see, 16 divided by 8 is 2. Log base 2 of 2 is just 1, because 2 to the 1st equals 2. No, yeah, 4 minus 3, definitely 1. So this rule also is seemingly sensible. It makes good sense. And then lastly, we have the power rule for logarithms. If you have the log base b of something to a power, I like to think of bringing that power down in front. This is equal to a times log base b of x. And the way I kind of think about why this rule works is because you're really just using the first rule, the rule for the log of a product, multiple times. Let me show you an example. Let's say we had log base b. Let's pick a real number, James. Let's say log, since b kind of looks like 6, let's say it's log base 6 of 7 squared. I don't know what log base 6 of 49 is. No one should really, unless you have a calculator built into your brain. But I know that log base 6 of 7 squared is just 7 times 7. So I'm going to rewrite this as log base 6 of 7 times 7. But then I can use the product rule for logarithms and say, oh, log base 6 of 7 times 7 is log base 6 of 7 plus log base 6 of 7. And when you add something to itself, it's like multiplying that thing by 2. And 5 plus 5 is 2 times 5. Log base 6 of 7 plus log base 6 of 7 is 2 times log base 6 of 7. So look, that exponent of 2 eventually traveled all the way down to the front and ended up right there. So that's what I think of as the power of logarithms. If you've got a log of something all raised to a power, you can always bring that power down the front. I will tell you, you use all of these rules relatively frequently in calculus. Like, especially if you're trying to take a derivative of something with a logarithm, you often use these three rules to expand it into many simpler logarithms, because a simpler logarithm is easier to differentiate. So that's probably actually the main thing we'll get to in the next class, is how we take a thing that's somewhat complicated and expand it into a much simpler expression, or a lot more numerous simpler expressions. But today we're kind of going in the other direction. We are going to take things that are very expanded out and try to compress them into one expression of logarithms, because that allows us to solve equations. So for example, if I want to evaluate 1/2 log base 6 of 81 plus 2 log base 6 of 2, I'm going to try to compress that all into one thing. So we're going to compress or smash it all together into one logarithm. So if you're ever trying to put multiple logarithms together into one logarithm, they first all need to have the same coefficient. Specifically, you really want them to have a 1 out in front. So I don't want that 1/2. I don't want that 2. I'm going to kind of do the reverse of this rule and bring them back up as powers. So I'm going to rewrite 1/2 log base 6 of 81 plus 2 log base 6 of 2 as log base 6 of 81 to the 1/2 power plus log base 6 of 2 squared. Because that is something that now I can smash those two things together. But before I do that, though, I could probably simplify those insides. 81 to the 1/2 might not look very familiar, but the square root of 81 should. The square root of 81 is just 9, and that is the square root of 81. It's just written in the other way of writing the power. So this is really log base 6 of the square root of 81 plus log base 6 of 2 squared is 4. And that's going to be log base 6 of 9 plus log base 6 of 4. And once again, we probably don't know what those things are. I don't know what log base 6 of 9 is. I don't know what log base 6 of 4 is. 6 to some power is equal to 9. It's some weird, irrational number that goes on forever and ever and ever. But I can put these together and say, oh, well, that's going to be log base 6 of 9 times 4. And 9 times 4 is a number I know how to take the log base 6 of, because 9 times 4 is 36. And log base 6 of 36 is right. So all of this kind of gross large expression here simplifies just down to 2 at the end. So sometimes it really does pay to take a long logarithmic expression and condense it down into something much, much simpler. The other reason we sometimes want to condense multiple logarithms into one logarithm is to solve an equation. So let's look at the next page. Let's say we want to, I should call it my note too. So we want to solve for x. We have log base 5 of x minus 3 plus log base 5 of x plus 1 equal to 1. So we have to be able to solve this logarithmic equation, we really have to condense all the logarithms into one logarithm. So I'm just going to rewrite this left-hand side of this equation as, well, since the logs are added together, it's going to be log base 5 of the inside parts, or the arguments, multiplied together. So x minus 3 times x plus 1. So we've got log base 5 of x minus 3 times x plus 1 equal to 1. And I would probably multiply out the inside first before I do anything else. So let's rewrite this as log base 5 of, let's see, x minus 3 times x plus 1, x squared. I'm going to get a minus 3x and a plus 1x. That's going to be a minus 2x. And then a minus 3 plus 1, or minus 3 times plus 1 is minus 3. Equal to 1. Okay, the next step is where people somehow often like to make an error. So I've seen many times people be like, okay, that means x squared minus 2x minus 3 equals 1. They just kind of forget about the logarithm. We can't just forget about the logarithm. The logarithm is there, but we can rewrite this as an exponential equation. So we're going to rewrite it. Rewrite as exponential. Okay, so if I have log base 5 of x squared minus 2x minus 3 equal to 1, what's my base? What's the exponent? 1, and it's equal to the thing we haven't used yet, which is x squared minus 2x minus 3. Okay, 5 to the 1 is just 5. Whenever we're solving something like this that's non-linear, right? It's a second degree or higher thing, we're going to bring everything to one side. I might as well bring everything to the right since almost everything is already on the right. So let's just subtract 5 from both sides and get 0 on the left. And x squared minus 2x minus 3 minus 5 is minus 8. And then if the person writing the problem has done a good job or is nice, this will factor. So let's see, this does factor. The factor says x minus 4 times x plus 2. Okay, so I want to make an important point here. Our possible, emphasis on possible, our possible solutions are x equal to positive 4 and x equal to negative 2. But what might happen is they might both be solutions. One of them might be a solution, or neither of them might be solutions, because they might not be in the domain of the original expression. Because we said last time, I know we said it very briefly, but we did say at one time last class that you can only take a logarithm of a positive number. So let's ask ourselves, if we plug in x equal to 4, is 4 minus 3 positive? Cool. Is 4 plus 1 positive? Great, then it's good to go. You don't need to check that it actually works, because if you've done the work correctly, it's the right answer. So yes, we want this one, yay. On the other hand, is negative 2 minus 3 positive? No, we're done. You're not a solution. That's called an extraneous solution. And here's why it came out as a possible solution. If you plug in the negative 2 right here into this condensed version, it totally works. Negative 2 squared is 4. Negative 2 times negative 2 is also 4. So 4 plus 4 is 8. 8 minus 3 is 5. And log base 5 of 5 is totally 1. So it works here, but it has to work in the very original expression to technically be a solution to the original equation. So whenever you're dealing with these kind of logarithmic equations and you get solutions, you do have to check them in the original expression to make sure they're actually in the domain. Kind of a pain, not bad. Just as a note, it's not always going to be that the negative one doesn't work and the positive one does work, because maybe my thing, right? Maybe my, well, we'll see. I think we'll see. None of my examples show that, unfortunately. I'll make up an example and write it up later and show you that you can have negative numbers that totally work as an answer and positive numbers that totally don't work as an answer. So don't fool yourself into thinking it's always the negative ones that don't work and the positive ones that do work. Although that's probably what we're going to see in this next example. So yeah, my examples are not good for that. I'm sorry. I'll come up with some more. All right, again, solving for x. Again, we want to compress our logarithms into one log, but just like the not last example, but the one before that, before we can compress the logs together, we need to deal with that 2 out in front. So I'm going to rewrite this as log base 3 of x squared minus log base 3 of x plus 6 equal to 1. And now we can condense those into one logarithm. So it's going to be log base 3 of, since it's a subtraction, it's going to be the first thing divided by the second thing. So it's log base 3 of x squared divided by x plus 6 equal to positive 1. We've condensed as much as we can. Now we get a rewrite. We're going to rewrite this as, I want you all to rewrite it. I'll give you 30 seconds to rewrite. I don't have a second on it. I'll give you 30 seconds to rewrite it as an exponential equation. Darn it, don't go for that. Why do you do that to me? Oh, it's been more than 30 seconds. Okay. So let's see. So I'm going to rewrite this as 3, my base, to my exponent 1 equal to x squared over x plus 6. And if I was going to try and solve this, I would probably then multiply both sides by that denominator. So I'm going to say, all right, I've got 3 times x plus 6 equal to x squared, or 3x plus 18 equal to x squared. I'm a big fan of having my highest power of x have a positive coefficient. So although you might say, I want to bring x squared to the left and make it negative x squared plus 3x plus 18, that is not what I want to do. I want to bring everything to the right.
X squared or divided by x plus 6. And you can't like, oh, I was about to say, like, can you just like divide x squared by x and that's the result?
We cannot. No, unfortunately, we cannot just divide x squared by x. Because so what I want to point out is this doesn't say x squared divided by x and x squared divided by 6. It's x squared divided by x plus 6, and you're kind of stuck with x plus 6. There's nothing you can do with that. So if your denominator has addition in it, there's no way to kind of separate things. On the other hand, just as a kind of contrast to that, if you have something like x squared plus 6 divided by x, then you can totally divide each thing by x. Okay, you've got x squared divided by x plus 6 divided by x, and then x squared divided by x, and that's what it is. That works, but the other way does not. So I'm going to bring everything to the right hand side and get 0 on the left equal to x squared minus 3x minus 18. It's totally fine to bring it all to the left. I just don't like having a negative x squared. If I did bring everything to the left, I would multiply both sides by -1. So I didn't have a negative x squared. So just don't like dealing with it. And you don't have to. You almost never have to actually deal with factoring a negative x squared. So then we factor. We're going to get 0 equal to x minus 6 times x plus 3. Because -6 and +3 multiply to -18 and add up to -3. So then our possible solutions are x equal to 6 and x equal to -3. And although I certainly did say that it's not always going to be the positive one working and the negative one not working, in this example, the positive answer does work. Because if you plug in 6, log of 6 is a positive number, and 6 plus 6 is a positive number. So that checks out. We can always take the log of a positive number. So that one's a yay. On the other hand, if you plug in -3, so I will point out, if you plug in -3 here to x plus 6, it's totally fine. -3 plus 6 is +3, and you can totally take the log of a positive number. But if you plug in the -3 here, that's where things go awry. So it doesn't work. You can't get an, that's not an actual solution. Yeah.
Like when you're starting a negative number, when is it that it's still negative and when is it that it's positive?
So I think I know what you're asking, but let me know. So the difference, I think you're asking about the difference between like this versus this.
Yeah, I guess.
Okay, so when I read this, I read this as -3 quantity squared. So I'm squaring the number -3. So this really means -3 times -3, which is going to be +9. On the other hand, this here says I've got 3 squared and then I want the negative of that. So this is really the negative is happening last, and my 3 squared is 3 times 3. So 3 times 3 is 9, and then it's the negative of that, which is -9. But you can't, I agree, it can be dicey sometimes. You have to be extra careful when you have negative numbers squared. And it especially comes up a lot of the time when you're finding like the y coordinate of the vertex of a parabola. Because often your input is a negative thing and then you're squaring it, or sometimes it's the negative x squared of your parabola. So just, it does require being a little extra careful. I should say, just along with this, if you're, just as a quick aside, if your parabola is something like -x squared plus 6x plus 1, I don't know what it is, What I'm going to tell you is whatever you plug in for your x coordinate of your vertex, whatever that happens to be, if I plug in something here, I'm going to square it first, which will be positive, but then it's going to be the negative of that. So this negative x squared always gives a negative output. And then you add some other stuff to it. But this part here, this here, that's always negative, no matter what value you substitute in for x. Cool. All right. I'll put that at the end of the notes that I posted later on. I know. I was checking something just to see one thing. So let's solve some more things with logarithms. The logarithm kind of day. So most of the time, I shouldn't say that. A lot of the time when you're solving things with logarithms, you're going to rewrite it as an exponential equation. It often is helpful to go from what you've got to the other kind of way. So we're going to go from logarithmic equations to exponential equations and vice versa. From exponential equations to logarithmic equations. So this first example, log base 8 of 32 equal to x. Although there are other ways to solve it, I'm going to rewrite it. I'm going to rewrite it as 8 to the x equal to 32. And in this case, at least, we could totally use the fact that 8 and 32 are both powers of a common base. 8 is a power of 2, it's 2 to the third. And 32 is a power of 2, it's 2 to the fifth. And then 2 to the third of the x, we multiply those powers together and get 2 to the 3x. The 2 to the fifth still stays as is. And I should say here, I typically at this point just say the powers have to be the same. So basically the same. Another way to say what's happening here is though, if you really wanted to, you could take the log base 2 of both sides. So I'm going to show you two different ways to get here. One way is just to say you've got 2 to the 3x equal to 2 to the fifth, then 3x equals 5. Which is what I would recommend. This is, oh, sorry, thank you. I would certainly prefer to do it this way myself. So x is going to be 5 thirds. But sometimes it might pay to think of this as, well, if I've got 2 to the 3x equal to 2 to the fifth, maybe for some reason, I want to take the log base 2 of those sides, because maybe that's just a way I see it better. So if I take log base 2 of 2 to the 3x equal to log base 2 of 2 to the fifth, this actually is going to show us something a little worthwhile. So let me ask you all a question. I'm going to ask it two ways before I go. So I want to find log base 2 of 2 to the fifth. Or in other words, 2 to what power equals 2 to the fifth? 2 to what power equals 2 to the fifth? What's it have to be? Has to be 5. 2 to what power equals 2 to the fifth? The power has to be 5. The other way you can justify this is just you can use the power rule and bring down that power. That power of 5 can come down in front. And then you've got, I don't think you need to do this step, but then you've got 5 times log base 2 of 2. And log base 2 of 2 is 1, because 2 to the first power is equal to 2. On the left-hand side, you could also bring down the 3x power, although again, you don't have to, and say, oh, I have 3x times log base 2 of 2. But log base 2 of 2 is also still 1. So really, you have 3x equal to 5, which means x is going to be 5 thirds. But the thing that I think was most useful about this example was the thing I said right here, where we said, what's log base 2 of 2 to the fifth? Oh, it's just 5, because you're asking 2 to what power equals 2 to the fifth. And this is a thing that is generally generally true. If you have log base b of b to a power, the answer is just that power. All right, let's look at the next one. 10 to the x equals 2. Well, I guess I would rewrite it as a logarithmic equation. So what's my base? My base is 10. And I'm going to write the base here at first, but then I'm going to write it without the base in a second. So log base 10 of 2 equals x. I think we're done. We solve for x. There's nothing else you can do with this. Specifically, I do not want or expect you to use a calculator to give me a decimal approximation. That's the exact answer. That's the answer we want. I will point out, since it's log base 10, that's the base we don't have to write. So you could really write this as x equal to just log of 2. Okay. So now for this next one, this next one we have exponents on both sides. E to the x equals 10 to the x plus 1. So typically, if you have exponents on both sides of an equation, the way people often approach these sorts of things is by taking a logarithm of both sides. And the standard usual choice for which logarithm we pick is the log base e, aka the natural log. So we're going to take log base e of both sides. And I'm going to kind of say it in two different ways. One way is just to say I'm going to take log base e of e to the x equal to log base e of 10 to the x plus 1. All right, so just like before, when we said log base 2 of 2 to the 5th has to be 5, because you're saying 2 to what power equals 2 to the 5th? What's log base e of e to the x going to be? We're saying e to what power equals e to the x? It has to be x. So we've got x equal to, I'm going to rewrite the log base e as the natural log. So I want to point out, this isn't magic, this isn't voodoo, I'm not doing anything crazy here. I'm just using an abbreviation. People for some reason get all bent out of shape about this, but log base e, I'm just a lazy mathematician. I don't want to write 4 letters, I want to write 2 letters. It's the same thing. Natural log. Same as log base e. Now, what I want to point out to everybody is we could have gotten here a different way. Instead of taking the natural log of both sides, we could have said, I'm going to rewrite this as a logarithmic equation. So if I think about the fact that I have e to the x equal to a thing, I could rewrite this as, well, e to the x equal to a thing means I should have log base e of that thing equal to the power. Right? I'm really just rewriting it. I'm taking it from an exponential equation to a logarithmic equation. And note, those are literally the same equations. X equal to the natural log of 10 to the x plus 1, x equal to the natural log of 10 to the x plus 1. I should also point out, I'm not done. If your answer for x has some x's in it, we're not done, right? We can't say that x is equal to something. We're actually trying to solve for the value of x. You can't have x's in your answer. So we have to do some more work. So the only thing I'm allowed to do at this point, or the only thing that makes sense to do, is to bring the x plus 1 down in front. And that is often why you take a logarithm of an expression, is because you've got some variables up in the exponent and they're a problem. You want them not there. So you take the logarithm of both sides so then you can bring them down. So I'm going to bring down the x plus 1 and say x equals x plus 1 in parentheses times the natural log of 10. Now, I want to solve for x. So what I'm going to do is I'm going to distribute the natural log of 10 to each of these terms here. So I'm going to have x equal to x times natural log of 10 plus 1 times natural log of 10. I don't think I need to write the 1. So x times natural log of 10 plus 1 times natural log of 10. And then I'm going to gather all the things that have x's on the same side of the equation. So I'm going to get x minus x times natural log of 10 equal to natural log of 10. Now, be careful here. X minus x natural log of 10, the x's don't cancel out. It'd be kind of like saying x minus 3x and the x's cancel out. You would have negative 2x there. Same kind of deal here. Instead of canceling them out, we're going to make the better choice and we're going to factor out an x or divide out an x. What's x divided by x? And x natural log of 10 divided by x is just natural log of 10. So I'm pulling out the x. And notice if you distributed that x back in, you would have what you started with. X times 1 is x. X times natural log of 10 is x natural log of 10. still equal to natural log of 10. And finally, the last step is going to be to divide by, whoops, that pen is not looking good. Divide by 1 minus natural log of 10. So these terms do cancel because they're the same and they're being multiplied. So I end up with x equal to this quotient, the natural log of 10 divided by 1 minus the natural log of 10. That is as far as we can get, as simple as our answer is going to get. Okay. Yeah. So here's what I say. When you have an equation, you're allowed to, with some exceptions, to always do the same thing to both sides of the equation. So if two things are equal to each other, it is totally fine to multiply them both by 5, or to divide them both by 3, or to add 7 to them, or even, as long as they're positive, to take the square root of both of them, or to do e to the them, or take the natural log of both sides of them. So there's a lot of things we're allowed to do to both sides of the equation. You're not allowed to multiply both sides by 0, right? That's what you can't do to both sides, because that just says, oh, 0 equals 0, great. So the kind of impetus for why we take the natural log of both sides is because I want those variables to move out of the exponents. Taking a natural log allows me to bring them down. Why natural log instead of log base 2 or log base 3 or log base 10? Because it's the most common logarithm, and I only have to write 2 things instead of 4. It's partly laziness. I mean, I joke a little about that, but it's really mostly because it is the most common logarithm people use. If someone says pick a logarithm, if you're talking to a math person, they're going to say natural log. That is the logarithm they want. It's the nicest one for a lot of reasons. Its derivative is the nicest, has some other great qualities. So natural log is the one people are going to pick. Even if E wasn't one of my bases, like in a couple questions from now, we'll see another example where we're still going to pick the natural log just because it's the natural log. It's the one we like it the best. Okay. Yeah. So, but definitely the reason we're taking the log of both sides, regardless of which base, is because we want those x's to come down out of the exponent. All right. I think this, oh, good job. I think this was, no, yeah, I think this was very close to, if not the question we didn't get to on the last homework, on the last class. It's off by a negative sign, which is totally fine. Good. I didn't spend time doing that. Great. So I want to solve log base x of 27 equal to -3/2. So what am I going to do? I'm going to rewrite it. I'm going to rewrite it as x to the -3/2 equal to 27. I'm trying to solve for x, right? That is all. I mean, typically, if someone says solve an equation and there's a variable, you're trying to isolate that variable. If I want to get x by itself, if x is by itself, what's the power on it that we're never actually writing? Is it 0 or is it 1? 1, right? X to the 1 is x. X to the 0, as long as x is like a positive number. X to the 0 is 1. So whenever you're writing x, it's really x to the 1. So if you're trying to solve for x, you want to get x to the 1. So what I want to do here is I want to make it so that the power on x is the first power. Okay, so just like before, when I took the natural log of both sides, I'm going to do something to both sides of this equation. Specifically, I'm going to raise both sides to a new power, a power that's going to undo the -3/2. So I'm going to raise both sides to the reciprocal power, -2/3. Reciprocals always retain the sign. So if you have a positive number, its reciprocal is a positive number. If you have a negative number, its reciprocal is a negative number. Okay. The reason we did that is because when you have a power to a power, we get to multiply the powers. So on the left-hand side, kind of too big there. All right. On the left-hand side, we have x to the negative 3/2 times negative 2/3. And on the right-hand side, I'm just going to leave it as 27 to the negative 2/3 for a second. Okay, so this is where we all have to be on board. Negative 3/2 times negative 2/3 is just 1. Or if you like, it's 6/6, which is 1. Maybe you say negative 6/6, right? But it's definitely 1, right? This number here, that is just 1. That's why we did that. So if you're ever trying to solve x to a power equal to something, raise both sides to the reciprocal power. It's almost always going to work. There might be some times it doesn't work, but whatever. Most of the time it works. So now I've got x to the first. I'll write one more time. And now I need to deal with this, because even though this is technically an answer, it can be simplified. Because I can say that's 27. Ooh, let me ask you all. Do I want to take 27 squared first? Or do I want to do the cube root of 27 first? You almost always want to do the root first. You could square it. 27 squared is 729. And then the cube root of that is going to be 9. And I only know that because I've done it the other way so many times. Because the other way is 27 to the 1/3 power, and then I still have a negative second. So notice here how I'm kind of undoing the multiplication of powers, right? I'm saying negative 2/3 is negative 2 times 1/3. I mean the 1/3 power first and the negative second power second. So then you guys told me to do 27 to the 1/3 because what do you know it's equal to? Right, it's 3. The cube root of 27 is definitely 3. So now I have x equal to 3 to the negative second. And you can either do the squaring part first or the negative part first. So when you have a negative power, it doesn't mean you get a negative answer. It means you get a what? Yeah, you get a fraction, you get a reciprocal answer. So I think I'm going to write this as x equal to 1/3 to the positive second. And then finally, x equals 1/9. So it's kind of weird because, as I said last class, most of the time when you deal with a logarithm, your base is a nice positive integer or the number e. It's kind of strange to have a base of 1/9. It's not allowed, it's just not typical. So what we've said here is log base 1/9 of 27 is equal to negative 3/2. Again, just a little strange, right? That's something we don't typically write because usually we think of bases as being nice positive integers, but they don't have to be. Yeah. Totally, we could have done that part first. You could have, right, straight from here, you could have said this is 1/27 to the 2/3 and then worked on it from there. The order you do things in, I won't say it doesn't matter because, right, like we all decided we want to do the cube root before we did the squaring, but you totally could have done the reciprocal anytime you wanted. Yeah. And I probably would have chosen to do it that way if I thought about it more. Yeah. The negative, so when I look at the power negative 2/3, I'm seeing the numerator being like a power, right? Like I have the 2 as, I'm ignoring the negative for a second here. If I had a 2/3 power, I'm thinking, oh, I'm squaring something, but I'm also doing the 1/3 power, which is the cube root. So I'm breaking it up into the denominator part, which is the root part, and the numerator part, which is the power part. So we all decided, and it's usually the right call to do the root part first. So we said, I'm going to do 27 to the 1/3, but then I still have the negative 2 part left. And the way I'm breaking this up is saying, if you have a power to a power, what do we do with those powers? Do we add them or do we multiply them? I should do it. We multiply them. And 1/3 times negative 2 is negative 2/3. So that's how we're getting from this to this. It's saying, oh, we can break it up as multiplication and then do power to a power. All right, let's look at these next two, which are definitely a little funky. So I've got, let's see what I've written. I want to see what I've got one other page here. Oh, that's interesting. Oh, okay, I see. Great. All right. Yeah, okay. Just like I thought I did. So I've got 5 to the 2x minus 3 equals 4. And I will certainly agree that you could use a log base 5 here, right? I could totally rewrite this as log base 5 of what? Of 4. equals 2x minus 3. That would be a completely valid way of approaching this problem. And then you can solve for x, right? In fact, let's do it. We're going to do it both ways. So if I add 3 to both sides, I get 3 plus log base 5 of 4 equal to 2x. And then finally divide both sides by 2. I get 3 plus log base 5 of 4, all divided by 2 equal to x. And that is a completely valid answer. And I'll say it's not even bad. The only issue with this answer is, unless you have some calculators probably have this button at this point, but a lot of calculators don't have a log base whatever you want of whatever you want. Most calculators typically, at least more easily, have a natural log and a log base 10. And log base 5 you have to like hunt for, or you have to use another formula called the change of base formula and then do some more math inside your head. So while this is totally fine, if you actually wanted to get a decimal approximation, it can be a little bit of a pain, which is why we often default to using the natural log, because the natural log is going to be on any calculator that has, unless it's like one of those like 4-function calculators, right? Natural log is like the first logarithm function, maybe log base 10 on your calculator. So you could do this, or we can take the natural log of both sides. So the natural log of 5 to the 2x minus 3 equals the natural log of 4. Right? Again, I really want to kind of emphasize, if you have an equation, it is totally cool to do the same thing to both sides of the equation. I should also mention, I am not multiplying by the natural log, just like we don't multiply both sides by the square root. Right? If you have x squared equal to 9, you're not multiplying by the square root. You are taking the square root of the stuff on each side. We are taking the natural log of, right? We are doing a thing to another thing. We're not multiplying by something. So we're evaluating this function at this, and then we're going to use our rules. I'm going to bring that power down in front. So I have 2x minus 3 in parentheses times the natural log of 5 equal to the natural log of 4. You could go a couple different ways here. Yeah, which way would I like? You could either distribute the natural log of 5 first, or you could divide both sides by the natural log of 5. I'm not really sure what I think is better. I'm probably going to distribute though, because that's my usual go-to. So let's go ahead and distribute. But if you wanted to first, you could totally divide both sides by natural log of 5, and then add 3 to both sides, and then divide both sides by 2. But then you get fractions and fractions, which I don't like. So I have 2x natural log of 5 minus 3 natural log of 5 equal to natural log of 4. I'm trying to solve for x, so I want to isolate x. This is the only thing that has an x in it, so I'm going to add the 3 natural log of 5 to both sides. So 2x natural log of 5 equals the natural log of 4 plus 3 times the natural log of 5. And if I want to isolate x, what am I going to divide both sides by? Yeah, 2 natural log of 5, exactly. So we're going to divide both sides by 2 natural log of 5, because that's going to get rid of the 2 natural log of 5. And so our final answer is x equal to natural log of 4 plus 3 natural log of 5 all over 2 natural log of 5. Which I will totally admit looks a bit different than the other answer up there. They are the same. They just look different. All right, one last one here. Ooh, this one's especially challenging because it's got variables in both exponents and bases that are not particularly lovely. Once again, if we have something like this, you want to use the natural log. Especially this one, right? I wouldn't want to be like, well, should I pick log base 3 or log base 5? We can go either way. I'm just going to pick the natural log because it's the one we use. So natural log of 3 to the x plus 1 is equal to the natural log of 5 to the 2x. I will warn you, this one does get a little bit messy. So we're going to bring down the powers on both sides. So I'm going to have an x plus 1 in parentheses. So make sure that when you bring down those powers, if it's like something plus something or something minus something, you put parentheses around that so that when you have the parentheses around that, you know that you're going to have to distribute this natural log of 3 to each of those things. And then on the right-hand side, I just have 2x times natural log of 5. No distribution needed on the right-hand side because I don't have things added together or subtracted together. All right, so on the left-hand side, I'm going to get x times natural log of 3 plus 1 times natural log of 3. Oh, that's the left-hand side. I still need the right-hand side. Equal to 2x times natural log of 5. So whenever you're trying to solve for x or whatever, y, whatever your variable is, you always want to, if you have an equation like this, we're always trying to group all the things that have your variable on one side and all the things that don't have your variable on the other side. And while I would usually pick the left side for my variable, here I see that the right side, all the terms on the right have an x in them. So I might as well move my things that have x to the right-hand side. Since there isn't anything from the right, I have to move back to the left. It doesn't really matter, but I'm just trying to not do a million steps if I can do less. So I'm going to say on the left-hand side, I'm just going to have natural log of 3. And on the right-hand side, I'm going to have 2x times natural log of 5. And I'm subtracting x natural log of 3 from both sides. And the whole reason for getting all the things that have x's on one side is then you can factor out an x. So I'm going to factor out an x. So I have natural log of 3 equal to x times the same thing I've already written above it, except without the x's. So instead of writing 2x natural log of 5 minus x natural log of 3, I'm just saying, well, now I'm going to have 2 natural log of 5 minus natural log of 3. I'm dividing out the x, factoring out the x. Okay, it's a little hard to read. Zoom in there a little bit. Finally, we divide both sides by whatever is multiplying x. So we take that equation and say, okay, well, now I'm going to have x on the right. On the left-hand side, I'm going to have natural log of 3 divided by this whole thing here. So I'm going to have natural log of 3 divided by 2 natural log of 5 minus natural log of 3. I will point out that some people, for some reason, like to simplify this even more. I don't think you need to. Meaning, here's what I mean by that. Some people, not me, would say, well, you can bring this 2 up and get natural log of 5 squared, and then natural log of 5 squared minus natural log of 3 is natural log of 25 over 3. Don't do that. We don't need to do that. This is a totally perfectly fine, good answer right here.